For a century, vertical urbanism was anchored in North America, then East Asia. Now, construction velocity has shifted towards South Asia. Historical global databases relying on voluntary data submissions often underreport the actual inventory on the ground. To see the real scale of this shift, we have to look at local municipal registries. This chart shows active construction pipelines for buildings over 150 meters. Mumbai currently has over 200 skyscrapers under construction, more than Shenzhen, New York, or Hong Kong. Gurugram and Hyderabad show a similar trajectory, each with over 170 active projects. This construction is concentrated in specific metropolitan nodes, altering their physical profile. This vertical expansion is a distinct economic outcome, rather than a direct result of population growth. To understand why these skylines are rising now, we must examine the municipal rules, the institutional capital funding them, and the hidden geotechnical risks below. The skyline is a manifestation of invisible forces. To understand what is being built, we must understand the specific rules and the capital paying for it. The foundational metric for any skyline is the Floor Space Index, or FSI. It determines the total buildable area allowed on a plot. For decades, strict limits, like Mumbai's historic 1.33 FSI cap, resulted in short, dense, and overcrowded urban geometries. Recently, several municipalities shifted toward regulatory liberalization. Hyderabad, for instance, removed standard density caps by offering unlimited FSI for high-rise developments. This liberalization is governed by a specific regulatory mechanic, setback coupling. The amount of density a developer can build is directly tied to the amount of open space left around the building. For structures over 15 meters, the required setback increases. Once a tower exceeds 55 meters, the code requires a 16-meter setback on all sides, plus an additional half-meter for every 5 meters of height added. The shift toward unlimited density triggered localized land speculation. In primary growth corridors, land prices rose to between 30 and 35 crore rupees per acre. Because the land is so expensive, developers must maximize vertical density on smaller footprints to recover their acquisition costs. This high density often runs ahead of municipal infrastructure, creating bottlenecks in road networks and sewerage systems at the base of these towers. Deregulating density was intended to manage urban sprawl and land costs. In practice, these rules favor the development of high-density luxury towers in prime corridors. Executing a construction pipeline of this scale requires significant liquidity. Developers currently face a projected construction funding requirement of over 92,000 crore rupees. This diagram shows the flow of that capital. Since traditional banks face limits on real estate exposure, developers increasingly rely on alternative investment funds, private credit, and non-resident Indians seeking wealth preservation assets. This capital is not being deployed evenly across the market. In the first half of 2024, premium housing launches grew by 30%, capturing nearly half of the total market share. Meanwhile, the sub-1 crore affordable segment contracted by 21%. Ordinary buyers are finding fewer options within their budget as developers pivot toward higher-margin projects. There is a distinction between housing need and effective purchasing power. While millions of households require homes, only a fraction can clear the financial hurdles created by rising land and construction costs. These two markets often coexist in the same urban geography, with luxury high-rises rising directly adjacent to informal settlements. This concentration of capital in high-rise booms has historically led to market friction. The Skyscraper Index suggests that super-tall projects initiated during periods of easy credit can lead to oversupply and financial distress. We see this friction in projects like Noida's Supernova Spira and Mumbai's Palais Royale. Complex financing and regulatory litigation left these structures incomplete for years. The capital markets are functioning efficiently to solve the wealth preservation needs of high-net-worth investors, but this efficiency is simultaneously reducing the supply of affordable housing. While financial metrics dictate the sky, physical limits dictate the ground. We must look at the conditions beneath the foundations. This map utilizes INSAR satellite data to show ground deformation. It reveals that 878 square kilometers of land across India's major cities are actively subsiding or sinking. The primary cause is groundwater extraction. When high-rise clusters extract water faster than aquifers can naturally recharge, the loss of underground pressure causes the soil matrix, the clay and silt, to compact and sink. Different soil compositions react differently. Chennai's sandy clay is highly vulnerable to compression, while Mumbai's marine clay experiences localized sinking beneath heavy vertical districts. This leads to a structural risk called differential settlement. The ground rarely sinks evenly. If one side of a building drops faster than the other, it creates immense structural stress. That angular distortion can crack foundations, damage utility lines, and compromise the structural integrity of a rigid building. Research suggests that over 23,000 buildings in these subsidence zones could face severe foundation damage within 50 years if groundwater trends continue. Constructing high-density monoliths without the necessary municipal water infrastructure leads to localized structural risks as the supporting soil compacts. To manage these physical realities, engineers are deploying advanced structural techniques to mitigate risks from both soil settlement and seismic activity. Traditional construction in India relied on reinforced concrete frames with brick and masonry infill, a method that is relatively slow and heavy. Most new supertalls now utilize MIVN formwork, or monolithic aluminum formwork. Instead of using bricks, MIVN technology casts the walls, slabs, and columns simultaneously in a single concrete pour. This creates a unified, reinforced concrete shell. This monolithic structure provides better load distribution. In compliance with the IS 456 code, it allows the building to better resist the stresses of differential settlement and seismic forces compared to traditional masonry. There is an economic factor. MIVN technology reduces floor-to-floor cycle times from 21 days to 7, allowing developers to compress their construction timelines. While industrialized methods allow engineers to build taller and safer on unstable ground, they set a higher baseline for construction costs in Indian real estate. India's skyline is the result of a specific equation: high land costs and liberalized FSI, multiplied by premium institutional capital. This system is optimized for vertical density to manage land costs, but creates challenges for long-term affordability and geotechnical stability. Managing this growth requires a policy shift toward transit-oriented FSI, where permissible heights are coupled directly to the capacity of localized public transit and utilities. Approval systems must also integrate INSAR subsidence data and mandate aquifer recharge programs to stabilize the ground beneath these megacities. Finally, standardizing resilient, industrialized building codes can help ensure that the entire housing stock, not just luxury towers, is built to modern safety standards. The race to build the tallest skyline in South Asia is succeeding. But without realigning the rules of density, capital, and infrastructure, the project risks trading short-term growth for long-term geotechnical and social instability.